Okay, let's talk about linear approximations and differentials. Remember, linear approximation, all we're doing is finding the equation of a tangent line. Our linearization is the function at some specific point. We're always finding our linearization centered around some given x value. So it's our original function at some x value plus the derivative at that same x value times change in x minus x naught. This is just the equation of the tangent line. If we move this over to the other side, that would just be y minus y naught equals mx minus x naught. That's all it is. So we've got this function here. Make sure you are in radian mode. We're going to be in radian mode all semester. So we're going to find a few different things. We're going to find the function value. There's our x naught. So we're going to plug that in here to get f of x naught. Then we're going to take the derivative. You're going to have to use chain rule. We've got a function inside another function. Use chain rule to find f prime at x naught. And there's your x naught. So you're going to have your formula is going to have an x in it. You're going to have some number plus some number times x minus pi over, what was it? Pi over 2. That is your linearization. It's a formula. We're going to use that to estimate our function at a nearby point. So we've just built a tangent line that just touches this curve one time near the point x equals pi over 2, near that x value. So we could use that tangent line to approximate this function only around this point. That linearization, this formula we just came up with, is not going to do us any good at x equals 12, only for x values around pi over 2. 1.5 is kind of close to pi over 2. So that's our x value that we're using here and here. So we're going to plug 1.5 into this formula right there for x. Then we're also going to find the actual function value. We can get our calculator out and type this in. And those two answers should come out pretty close. Not exactly the same, but pretty close. Then we're going to find the error in that estimate. So, and I don't care about sign. Like, who cares who's bigger or smaller? Just absolute value, biggest minus smallest. See how far away your estimate was from the actual value. And your error should be pretty small. Okay, it's really the same question, but it's a different question. Now we're going to use differentials. So recall that really all we're doing is we're moving this to the other side and making that a change in y is approximately equal to your function value evaluated at some x value times some change in x. So first we got to figure out what function are we talking about here? Well, we've got volume of a right cone. So maybe we'll just Google that, volume of a right cone. Hey, there's our formula. Volume is pi r squared h all over 3. Really looks better if we write that as all over 3, like I did here. Then we're going to take the derivative of both sides. We're going to find our differential. So that dv, delta v, is approximately equal to the derivative of this thing. Now, we've got two variables in here, r and h. Who are we taking the derivative with respect to? We got to look back at the problem and see who's changing. The radius is the one that we're not quite sure of. There's some deviance, some derivation in the radius of this cone. So we're going to take the derivative of this. We're going to have to use power rule here. H is going to be held constant. Take the derivative of this with respect to r. And you get delta V as some formula times delta R, approximately. Then we know our initial. radius, we know our initial height, we know our delta R, we can approximate delta V. Keep in mind, word problems have word answers, meaning you have to have units on your answer. And we just found an error in the possible volume. So our answer should have units of volume. That's a good place to stop.